Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 47 of the course Theory of Computation. This is also the beginning of week 10. In this week, we'll see more about the class NP, and we'll also see NP completeness, right? So we'll first begin with a different characterization of the class NP, right? So in the previous week, in week 9, we saw that NP stands for all the computational problems or all the languages that that can be decided by a non-deterministic Turing machine in polynomial time, right? So that has a non-deterministic polynomial time decider, right? So in this lecture, we will see a different characterization for it, one that is based on verifiers, right? So to understand this characterization, let us take some examples. So in the previous lecture, we saw a couple of languages that are in NP, right? So one was SAT, one was 3-colorability, and one was subset sum. So if you recall the proof that these three languages were in NP. So in the case of SAT, what we did was to guess an assignment of the variables involved and then check that this assignment is a satisfying assignment, right? In case of subset sum, we guessed a subset of the given set and checked what is the sum of the given subset, right? So, and in 3-colorability, we guessed a 3 coloring, or we non-deterministically came up with a 3 coloring and checked whether this is a proper 3 coloring. So just to give you a bit more detail on one of these, let's say 3-colorability. Suppose there was a valid 3 coloring, then the valid 3 coloring will be one of the possible guesses that we will make, and hence we will accept, the non-deterministic Turing machine will accept. If the graph is not 3 colorable, whatever be the guesses, none of them will accept. So this is what I'm saying is that the algorithms that I've described is a proper correct non-deterministic algorithm, right? And the running time is all polynomial time. It's easy to see, right? So the point that I am coming to is that there is in all these three cases, there is a common framework. We guess something which is completely non-deterministic, and then we do some verification which is completely deterministic, right? So we have some non-deterministic choices made at the beginning, followed by an entirely deterministic process. So this is called guess and verify, where the guess stands for the non-deterministic part and the verify stands for the deterministic part. So now the very, very natural question to ask at this point is it the case that any non-deterministic Turing machine or any NP machine can be converted into something that does this, like guess and verify, right? So in these three cases, it was a guess and verify situation, but perhaps we could have non-deterministic Turing machine that makes some non-deterministic choices, then does something deterministic, and then again makes some non-deterministic choices. Or maybe it makes non-deterministic choices throughout, right? So now, can any non-deterministic Turing machine be converted into something where all the non-deterministic choices are made at the beginning, followed by an entirely deterministic process, right? So that's the question that we are trying to answer through this verifier model, right? So the answer is that yes, any non-deterministic Turing machine can be converted into a guess and verify non-deterministic Turing machine, and in particular we will see this guess and verify model specific to the class NP. Okay, so we'll first formalize this notion of guessing and verifying, and then see the characterization, right? So first we'll define what is a verifier. A verifier for a language is an algorithm V or a deterministic Turing machine V, such that the language is a set of all X whose membership can be verified by the deterministic Turing machine, right? So what do I mean by whose membership can be verified? So the language X, the L consists of all X, whose membership in L can be verified by V along with a string Y, meaning, so this Y helps in the verification that X is in the language. So right now it may seem a bit abstract, but it's easy to see once we have the example, right? Suppose X is a Boolean formula, right? And L is satisfiability, the class of or the set of all satisfiable Boolean formulas, right? So now so now if we are, so let's say Y is a satisfying assignment. So now given a satisfying assignment, I can just check, I substitute this satisfying assignment into the formula. So satisfying assignment means x1 is true, x2 is false, some assignment which satisfies the formula, right? So now given a satisfying assignment, it is easy for us to check that this formula is satisfiable. If we were not given a satisfying assignment, we may have to do some other thing, right? So we in this case could be an algorithm or a decider that just substitutes the given assignment which is given by Y, given assignment which is given by Y into the formula X, and then accepts if it is a satisfying assignment, if X evaluates is true on Y, right? In case of 3 colorability, X is a graph that is 3 colorable and Y is an actual valid 3 coloring, right? So now, and the verifier is a decider that actually assigns the proposed 3 coloring and then verifies whether it's a proper 3 coloring, right? So we will accept if the coloring given by Y is an actual 3 coloring of X, otherwise it will reject. So this is the role of Y, right? So a verifier is a device or a decider or a deterministic Turing machine that accepts X and with the support of Y, right? So Y is something that helps us verify that X is a member of the language, and a verifier is something just that conducts the verification. So verifier is entirely deterministic. It just has to check something check something. In the case of satisfiability, check that this assignment satisfies this formula. In case of 3 coloring, it checks that this coloring is an actual 3 coloring of this graph, right? So Y is sometimes called a proof or a witness or a certificate, right? So the thing is, why is it called proof or witness or certificate? Because Y is in some sense an evidence or a proof that X is in the language, right? So you want to know whether this graph is 3 colorable. So an actual 3 coloring is something that you can use to certify that this is X is in this graph is in the class of all 3 colorable graphs, or we can say the 3 coloring is a witness that this graph is a member of all the 3 colorable graphs, or a certificate of the same thing, right? So this is called a verifier. A verifier is a Turing machine that is able to verify the membership of a string X in the language with the help of a proof or a witness string or a certificate string Y, right? So the language is just consisting of X. The language is just a set of all satisfiable Boolean formula or the set of all 3 colorable graphs. Y is a proof or a witness or a certificate that helps us verify that the graph is 3 colorable or the formula is satisfiable, right? So why is this whole thing interesting? This is because to actually determine whether a given formula is satisfiable is hard, right? Because right now it's not clear how you will go about doing it. Maybe the only thing that you can do is brute force by checking all the possible assignments, right? This is one possibility, right? There may be slightly better algorithm, but not significantly better. There is no like efficient algorithm, right? So we don't know of any polynomial time algorithm. But suppose I give a satisfying assignment and then I ask you to verify that this formula is satisfiable. You can just substitute this assignment and see for yourself that it is indeed a satisfying assignment, right? So now in the second case, you are just asked to verify that this formula or this assignment satisfies this formula. This is something much simpler to do than to search the whole space of assignments and see if there is some assignment that satisfies this, right? So to verify, given an assignment, to verify that this is a satisfying assignment is much simpler than deciding whether it is satisfiable. Similarly for 3 colorability. to given a graph, to decide whether it's 3 colorable, one has to check all possible 3 coloring assignments, right? But given a 3 coloring, it's easy to verify that this is a valid 3 coloring, right? Given if it's a valid 3 coloring, it's easy to verify. So the point I am making is that it is much easier to verify something, right? So the existence of a y, which is existence of a proof, and the requirement to verify that x is in the language with y is much simpler than without being given anything to test if x is in the language, right? Verification of x being in the language with the help of y is much simpler, right? So that is the situation, right? So y is a proof or witness or certificate that helps us determine that x is in the language, right? And what is NP? NP is the class of languages, right, that have polynomial time verifiers, right? So this is the characterization of NP using the guess and verify model. So we earlier saw that NP is a class of languages that have a polynomial time non deterministic decider. Now I am saying it is a class of languages that have polynomial time verifiers, right? In other words, what do I mean by polynomial time verifier? So it's what we just discussed. So a language is an NP. So L is an NP if there is a polynomial time verifier algorithm for the language L. So again, just to elaborate it a bit more. So what do we want to have, right? What property do we want the verifier to satisfy? If x is in the language, there should be a y such that the verifier can verify the membership of x with the help of y, right? And in addition, so this is what we discussed as verifiers earlier, and in addition now I want everything to be polynomial time, right? So earlier in the definition of verifier I didn't say anything about polynomial time, but now that I am talking about NP, I want it to be polynomial time, right? So now, which means the verifier should be running in polynomial time, and also the length of y should be also in polynomial in the length of x, because if y is much longer, then the whole thing doesn't make sense, because the verifier runs in polynomial time in the length of x and y. So if y is much longer than x, then the verifier could take a long time, which again defeats the purpose. So L is an NP if there is a polynomial time verifier for L, right? And what should the verifier, what property do we want the verifier to satisfy? For any x that is in L, there should be a y which can be verified polynomially by the verifier, meaning the y should have a length polynomial, right? So length of y should be polynomial in the length of x, and v should also be polynomial time verifier, meaning a polynomial time deterministic Turing machine that outputs 1 when x and y are in the x is in the language. So 1 is like accept and as against 0, right? So think of this 1 as a Boolean output. So what is, so just to understand what is the negation of this? If x is in the language, this is the case. If x is not in the language, right? If x is not in the language, so if a graph is 3 colorable, there should exist a proper 3 coloring. If the graph is not 3 colorable, no matter what 3 coloring you try, none of them will be a proper 3 coloring, right? So for all the possible certificate strings, right, or for all the possible 3 colorings which are of polynomial length, right, Vxy should be 0, meaning whatever 3 coloring you assign should not be a proper 3 coloring, right, if the graph is not 3 colorable, right? So this is the negation. If x is in L, there should exist a proper 3 coloring, if L being the language of all 3 colorable graphs. If the graph is not 3 colorable, then no matter what 3 coloring you assign, it is not going to work, right? So, and just one exercise, one easy thing to do is to just compare with what is the definition of P. P is the class of all languages that have polynomial time deterministic algorithms, right? So if L is in P, then there is a polynomial time decider algorithm A such that whenever x is in the language, Ax should be equal to 1, right? So if x is not in the language, Ax will be equal to 0, right? So maybe I'll just write that also. X not in the language, Ax equal to 0. So notice this is much simpler because P is a much simpler class to understand. So if x is in the language, the decider will accept, and if x is not in the language, the decider will reject. Whereas in the case of NP, if x is in the language, right? If x is in the language, there is a certificate string that can be used by the verifier to verify that x is in the language. If x is not in the language, no matter what certificate string you try, it should not work, right? So otherwise it doesn't make sense, right? Because if x is not in, let's say if the graph is not 3 colorable, then whatever 3 coloring you try should not lead to a proper 3 coloring, right? So we saw two definitions. One was that NP is a class of all languages that can be decided by non-deterministic polynomial time Turing machines. And now this verifier model, NP is a class of languages that have polynomial time verifiers. So let's see the proof of this, right? So suppose L is in NP, meaning L has a non-deterministic polynomial time decider. Now we will show that it has polynomial time verifiers, right? So both directions of the proof are not that hard. Both of them are fairly straightforward. Okay. So suppose L is in NP, right? Which means there is a non-deterministic Turing machine N for L, right? And the non-deterministic Turing machine runs in n power k time, right? And that decides L. So suppose x is in the language, then that means that so when x is input to the non-deterministic Turing machine, there is a computation tree, right? If x is in the language, there is at least one accepting path, right? So let's say this is the accepting computation, right? So I am trying to highlight it here, and finally till here, right? So by the new color, the green or whatever, and so here we take the first option, here we take the third option, here we take the second option, here we take the second option, and finally we take the second option, right? So the point is, if x is in the language, there is a accepting computation path. There could be multiple accepting computation paths, but there is at least one accepting computation path. Now we want a polynomial time verifier for the language, right? So the verifier can do something like, so if I give you an non-deterministic Turing machine and ask you to tell you that there is a specific path, okay, this is the path, you first take the first choice. Basically I tell you this path, the path that we just marked here, I just tell you this path and then ask you to verify. You, instead of asking you to explore all possible paths, I ask you to verify, just traverse this particular path and see if it leads to acceptance. And that is one way to convince you that the string x is accepted by the Turing machine n, right? So again, the setting is that you have a deterministic Turing machine and I want you to verify that this non-deterministic Turing machine accepts x, but you don't have the bandwidth or the time to test all the possible computation paths and simulate the entire NTM n using your deterministic Turing machine, right? But I am telling you, don't simulate the entire thing. Instead, just walk through this path and check that it accepts. And if once you do that, then you can convince yourself, you can be sure of yourself that this string is accepted, right? So the only thing that I need to do is tell you the way to which path leads to acceptance, right? And this is the idea that we can use to prove this direction, right? So whatever I just said is what is the verifier algorithm, right? So what is the verifier algorithm? The verifier algorithm simulates the non-deterministic Turing machine on the input x, right? And but then the verifier is deterministic. It cannot simulate the entire non-deterministic Turing machine because then it will not be polynomial, right? So instead, it does not guess all the paths, or nor does it try to exhaustively enumerate all the paths. it just walks through one path. This path, or the path that it walks through, is specified by the Turing machine y, the string y. So y could be the string that says something like, y could be the string that says 1 followed by 3 followed by 2, etc., etc. So by this we are trying to encode that you first take the first option, then you take this third option, then you take the second, and so on, right? So the verifier Turing machine which is deterministic, just simulates n, but does not entirely simulate n. It only simulates one computation path of n, which is given by the string y. So y dictates which, or y is telling which path to simulate, and then if it leads to an acceptance, the verifier accepts, right? So given the non-deterministic Turing machine, there are many possible computation paths, and x is accepted if at least one of them accept. So y, the correct witness string is the identity of that path which leads to acceptance, right? If x is not accepted by the non-deterministic Turing machine, whatever y you give, it cannot be verified, right? So the verifier machine is simply simulator of n on the input, and whenever there is a non-deterministic choice, it looks up y to decide which path to take, right? That shows that if L is an NP, it has a polynomial time verifier. So clearly the verifier runs in polynomial time, because n is also polynomial time. Verifier just walks through one path of n, right? And verifier is deterministic, right? So that is one direction. The other direction is also not that difficult. It says that if a language is a polynomial time verifier, then the language is an NP. So suppose there is a polynomial time verifier for the language L. Let's say the polynomial time verifier is V, right? And let's say V runs in time n power k, right? Now we need a non-deterministic Turing machine for, so now to show this characterization that polynomial time verifier implies that the language is an NP. NP now is that it's a class of languages that have deciders that run in non-deterministic polynomial time. So we have to come up with a non-deterministic polynomial time decider, right? So what is the decider? The decider is a non-deterministic Turing machine that runs the verifier, right? But with what witness string, right? Because there is no witness string that we are telling, right? So what it does is it guesses the witness string, right? So the non-deterministic Turing machine just guesses a random, or guesses a non-deterministically a witness string y of the appropriate length, and then so initially it guesses the witness string and then runs or simulates the verifier on the input x and the witness string as guided by the witness string y, right? And then if v accepts the pair xy, then the non-deterministic Turing machine accepts, right? So suppose x is a string in the language, then that means that there is some witness string that would lead to the acceptance of x. Suppose if x is a 3-colorable graph, there is at least one proper 3-coloring which can be used to verify that the graph is 3-colorable, right? So if x is in the language, there is a y that will help us verify that x is in the language, right? Now the non-deterministic Turing machine, one of its many guesses would be the correct y, and so it will lead to acceptance. If the graph is not 3-colorable, no y is going to make the verifier accept, and hence all the non-deterministic Turing machine paths will lead to reject, right? So again, the non-deterministic Turing machine is very simple. It guesses the witness string and then runs v, the verifier Turing machine, on the string input string x and the guessed witness string y, and accept if and only if v accepts, right? So basically here the Turing machine is basically guessing y, right? So many possible guesses of y, and then followed by running of, so here it's y equal to something 0 0 0 0 and till y equal to 1 1 1 1, and then followed by running of the verifier. So then now v and so on, and then based on that you accept or reject. So this shows that if the language has a polynomial time verifier, then the language is an NP, right? So that completes the proof that, so we have shown both directions. If L is an NP, then it has a polynomial time verifier, and that if L has a polynomial time verifier, then it is an NP. So now this gives us now after the completion of this proof, it gives another characterization for NP. NP is a class of all languages that have polynomial time verifiers, right? So now if you want to show something is an NP, instead of showing that it has a non-deterministic polynomial time decider, I can also show that it has a deterministic verifier, right? You can verify the membership of a particular string in the language, right? So now we have another characterization for NP. Now just to kind of recap, or just to kind of revise, so what is the proof or certificate or witness, right? So y is the string y is the proof or the certificate or the witness. And in different problems, what was it? In the case of subset sum, the subset that adds up to t was that adds up to the target sum itself was the proof. In the case of three coloring, the proper three coloring was the proof. In the case of SAT or CNF SAT, the assignment that satisfies the formula was the proof, right? So these are all proofs that the given string, so in the case of subset sum, in the given subset, right, or given instance is a yes instance. In the case of satisfiability, it is a proof that the given formula is satisfiable. In the case of three colorability, it is a proof that the given graph is three colorable, right? So this is the proof here is something that is quite straightforward. In the case of subset sum, the correct subset sum that adds to the target sum, right? In the case of CNF SAT, is a satisfying assignment. In the case of three coloring, it's the proper three coloring, right? So that completes the characterization of NP, that NP is a class of languages that have polynomial time verifiers, right? So now this is another way to think of NP. Now I want to just quickly state and explain the proof of the fact that, so you may recall that in chapter 3 we said that every non-deterministic Turing machine has an equivalent deterministic Turing machine, right? So now one question that we can ask, now that we are bothered about time that it takes, how much time does it take for a deterministic Turing machine to run a non-deterministic Turing machine, right, or simulate a non-deterministic Turing machine, right? So it turns out that the answer is, if the non-deterministic Turing machine runs in t time, right, time tn, the deterministic simulator takes time 2 power order tn, right? So it's exponential time in tn, right? So that is one of the bounds. There are slightly better bounds in the literature, but this is a simple result. So how do we get this result, right? So it turns out that the proof is something that we have already seen, is the same proof that we saw in chapter 3, right? And to be precise, we saw it in lecture 31, where we said that every NTM has an equivalent DTM, right? Now all that we are doing is we are just going through the same proof and kind of computing the time taken for the simulation, right? So instead of so earlier we told the proof without really bothering about the time. So now we are going to measure the time of the simulation described in the same proof, right? So just to describe the proof, we wanted to simulate a non-deterministic Turing machine by a deterministic Turing machine, right? So what we do is we kind of consider the computation tree, right, and look at all possible computation paths, right? We look at all possible computation paths, and we accept if we find an accepting computation paths. And the thing was that we do this in a breadth first search manner. That is what we said in the chapter 3, right? We simulate everything to one level, then second level, and so on, right? So anyway, that particular detail is not very critical here, but because it's all deciders. But let's see the time complexity of this process, right? So before that, let B be the maximum number of children any configuration can have in this configuration tree, in this computation tree. Okay, so in this particular partial tree that I have drawn, the maximum children that any configuration has is this, the one that I have marked here. There is a configuration with 4 children, right? So B, let's say it's 4, right? And if a non-deterministic Turing machine is defined, right, the constant B only depends on the Turing machine, not on the input, right? So it doesn't really depend on the input, it just depends on the Turing machine, right? So this is something that that one has to understand. So now we know that the non-deterministic Turing machine runs in time Tn, which means this whole computation, right, from start to accept, from root to the leaf that is farthest, is time is of height Tn, right? And since every configuration can have at most B children, there could be at most B power Tn computation paths, right? So the maximum that can happen is from the root there are B children, from every B children there are further B children. So the second level there are B, the third level there is B square, fourth level there is B cube, and so on. So finally at the level Tn we have B power Tn possible leaves, right? So we have at most B power Tn computation paths, and each computation path is of length Tn or at most Tn, right? Each computation path is of length at most Tn. So to go through all these paths and to check all these paths, we need to spend B power Tn multiplied by Tn time, right? B power Tn multiplied by Tn time. And what follows is a very standard calculation. B power Tn, we can write it as 2 power log B multiplied by Tn, where this thing is in the exponent, and Tn we can write as 2 power log Tn, and by adding the exponents we get this, the third equality. And since Tn log B dominates log Tn, we can just write it as 2 power OTn. So the proof is very simple. The simulation of the NTM by the DTM is just by traversing the computation tree. The tree has height at most Tn because that is the running time of the NTM, and at each level of the tree it has B children. So the maximum number of computation paths to consider is B power Tn. So the running time is B power Tn multiplied by Tn, which simplifies to 2 power OTn, or which is upper bounded by 2 power OTn. Hence the upper bound on the running time of the simulation is 2 power OTn. So any non-deterministic Turing machine that runs in Tn time, the deterministic simulation takes exponential time of that. If the non-deterministic Turing machine runs in n time, the deterministic equivalent runs in 2 power order n time, which is quite bad, right? So it's significantly worse. That's why this is another reason why we don't why we prefer to have deterministic polynomial time algorithms, right? And finally, I just want to say one more thing, right? That this may or may not, this may feature in some of the proof. We may be assuming this. That's why I'm saying it at this point. So we mentioned this branching factor B, right, which is the maximum number of children any specific configuration can have. Suppose the branching factor is some number like 10, right? Now what the point is that we can without loss of generality, we can assume that every configuration has at most two children, right? At every stage we have at most 2 choices and not B choices. Why is that? That is because we can like a node has, let's say, 10 children. We can replace that one node with 10 children with a small tree. So where this node corresponds to this node here, right? And the 10 and this small tree will have 10 leaves, and these 10 leaves correspond to the 10 children here, right? So basically the point is that if the non-deterministic Turing machine has takes up to 10 choices, we can replace it every non-deterministic step with a step that takes at most 2 choices, right? So this is sometimes this is convenient in some proofs, like we can assume that b is equal to 2, right? And it does not increase the time too much, because if the like b is usually considered to be a constant. So now to build a tree with 10 leaves, the height required is 4, right? So the height required will be 4. So here I think I have marked 1, 2, 3, 4, 5 leaves. So maybe one more level we need to mark, right? So something, right? So the height required is 4, which is again a constant, right? So it's just a constant blow up for the running time of the NTN. Right? So initially, if it took Tn time, now maybe it's some Tn multiplied by log b time, right? Log b to the base 2. So asymptotically, it is the same, right? So that is all that I have to say in lecture 47, right? So first we saw the verifier model for NP, right, where we saw that every non-deterministic Turing machine, which or every language that can be decided by a non-deterministic polynomial time Turing machine has a polynomial time verifier, and if a language has a polynomial time verifier, then it can be considered to be in NP, meaning it has a non-deterministic polynomial time decider, right? So meaning what does it mean when I say that L has polynomial time verifier? There is a machine, deterministic Turing machine V, which runs in polynomial time, which can verify the membership of any string X in the language with the help of a proof string or a witness string Y, right? So that is the meaning that NP is a class of languages that have polynomial time verifier. So for instance, if L is a class of 3 colorable graphs, and X is the set, X is a 3 colorable graph, then Y is a 3 coloring that helps us verify that the graph is 3 colorable, right? If L is a class of satisfying Boolean formula, then X is a specific satisfiable Boolean formula, then Y is the satisfying assignment that we can use to verify that X is in the group of, or X is in the class of satisfiable Boolean formulas, right? And the 2 directions were both straightforward, right? And then we saw that a non-deterministic Turing machine that runs in Tn time can be verified, can be simulated by a deterministic Turing machine in 2 power OTN time. And then finally we said this the small fact about if you have a branching of big number, then we can replace it with a small tree where the branching is at most 2. And that's all I have in lecture 47. In lecture 48, we will see NP completeness, and we'll see reductions, and we'll start moving towards NP completeness. So see you in 48. Thank you.